Hi, everyone. Welcome to our ARSET training series, Spaceborne Lidar for Monitoring Vegetation, Structure, and Biomass using JEDI. Today is part one of our training series, Introduction to Full Waveform Lidar. My name is Savannah Cooley. I'm a researcher at NASA Ames Research Center with the Bay Area Environmental Research Institute in Mountain View, California, and I'm a trainer with the ARSET Ecological Conservation Team. Before we begin today's training, I'll say a few quick words about the ARSET program. The NASA Applied Remote Sensing Training, or ARSET program, provides cost-free training on the use of remote sensing observations, analysis methods, and tools. We provide training in several thematic areas, including agriculture, climate and resilience, disasters, ecological conservation, health and air quality, water resources, and wildland fires. ARSET provides trainings, both online or in person. Our online trainings are delivered in two formats, live and instructor-led, like today's training, or asynchronous and self-paced. Like NASA's free and accessible data, all of our trainings are offered at no cost. We try to offer trainings in more than one language whenever we can, and we only use no-cost and open-source software and data. We offer our trainings at a range of levels so you can find a training series that fits your level of experience and interest. Please visit us at our website to learn more. We'll start today by giving an overview of this training series, Spaceborne Lidar for Monitoring Vegetation Structure and Biomass using JEDI. One fundamental question that many of us are interested in is thinking about forest canopies and what's happening specifically beneath the canopy, which from many traditional satellites, we don't actually know because a lot of optical remote sensing instruments can tell us about, for instance, greenness of the canopy, but can't actually tell us any structural information or information about the understory. Spaceborne LiDAR can do this. Spaceborne LiDAR instruments, such as NASA's Global Ecosystem Dynamics Investigation, known as JEDI, measures forest structure across over 20 billion locations on Earth. Today, you'll learn to use this data. By the end of this training, you will be able to, first, identify the fundamental physical principles of LiDAR remote sensing, including the uses and limitations for terrestrial applications. Second, access and retrieve full waveform LiDAR data from public NASA repositories to visualize vegetation structure. Third, identify key JEDI products, including elevation, canopy height, vegetation structure metrics, and biomass across different processing levels and spatial resolutions. Fourth, access and visualize JEDI data related to elevation, height, vegetation structure, and biomass for specific areas of interest using openly available tools. Fifth, utilize JEDI standard biomass products at footprint and 1 kilometer scales to map forest resources. Sixth, access the open source OB1 Application Programming Interface, or API, to generate estimates of biomass change in areas of interest. Finally, seventh, identify how OB1 can be used to create baseline scenarios for forest carbon accounting projects. The only prerequisite for this intermediate level course is the ARSET training on fundamentals of remote sensing. Here we provide 3 other suggested trainings, as well as a resource from the Land Processes DAC, which has a number of data tutorials for JEDI. And the other 3 trainings are ARSET trainings. All of them are available on our training webpage. There are 3 parts in this training. In part 1 today, we'll introduce the full waveform LiDAR with theoretical background and 2 hands-on exercises using JEDI Level 1 and Level 2 data. Parts 2 and 3 will cover additional spaceborne LiDAR products from the JEDI mission, as well as biomass estimation. The homework opens on the last day of the training on November 6, 2025. It is due 2 weeks later on November 20th. A certificate of completion will be awarded to participants who attend all live sessions and complete the homework assignment before the given due date. And with that, we'll begin part 1, Introduction to Full Waveform Lidar. We have 2 instructors for part 1. Myself, my name is Savannah Cooley, and our second trainer is Nayara Pinto, who is a research scientist in the suborbital radar science and engineering section of NASA Jet Propulsion Laboratory. I would also like to acknowledge my fellow colleagues in the ARSET Ecological Conservation Team who have supported the creation of this training: Sativa Cruz, Juan Torres Perez, and Justin Fain. By the end of this session, participants will be able to, first, recognize essential physical principles of LiDAR remote sensing. Second, identify different types of LiDAR sensors. Third, assess the uses and limitations of full waveform LiDAR technology for terrestrial ecosystem management and conservation applications. Fourth, access public NASA repositories to retrieve full waveform LiDAR observations to visualize and quantify vegetation structure. If you have questions during today's training, you can put them in the Q&A box within WebEx at any time. At the end of the training, we will try to address as many questions as we can, and we'll post these questions and written answers to the training page within a week after the training. All right, let's dive into section 1, which focuses on the fundamentals of LiDAR remote sensing. Remote sensing systems can be classified into 2 fundamental categories: passive and active sensors. Passive sensors detect natural electromagnetic radiation reflected or emitted from Earth's surface, such as sunlight reflected from vegetation or thermal radiation from the ground. Examples include optical satellites like Landsat and thermal infrared sensors. In contrast, active sensors generate their own electromagnetic energy and measure the signal returned from the target. LiDAR, which is short for light detection and ranging, is an active remote sensing technology that uses laser pulses to measure distances and properties of objects and surfaces. LiDAR operates on the principle of laser altimetry, measuring the time it takes for a laser pulse to travel from the sensor to a target and back. The full equation governing LiDAR distance measurement is that distance equals the speed of light, which is a constant, multiplied by the time of flight divided by 2. The system emits short laser pulses, typically in the near-infrared spectrum at 1064 nanometers, and precisely measures the time delay of the returned signal. This time of flight measurement, combined with the sensor's position and orientation, allows for the calculation of 3-dimensional coordinates of the reflecting surface. LiDAR's ability to penetrate vegetation canopies and provide 3-dimensional structure information makes it sensitive to several biophysical parameters. Elevation and topography is the first that I'll talk about, where LiDAR can create high-resolution digital elevation models, referred to often as DEMs, by measuring ground returns beneath vegetation canopies. The difference between the highest vegetation return and the ground surface provides direct measurements of canopy height, which is another key parameter often used for forest biomass estimation. LiDAR captures the 3-dimensional distribution of vegetation elements, revealing canopy layers, understory density, and structural complexity that cannot be observed with passive optical sensors. These structural measurements support forestry applications, wildfire applications, and conservation applications. LiDARs focused on terrestrial studies operate at either green or near-infrared wavelengths. The frequencies of these wavelengths, unlike microwave frequencies, cannot penetrate through clouds. LiDAR for terrestrial applications uses the near-infrared lasers like JEDI's 1064 nanometer laser because it reflects strongly off of vegetation. In contrast, bathymetric LiDAR uses a green light laser because that wavelength effectively penetrates water. On this slide, you can see a list of some of the available LiDAR instruments that include both spaceborne and airborne instruments, firing in the near-infrared as well as in the green portion of the electromagnetic spectrum. LiDAR systems can be deployed on various platforms, each offering distinct advantages. Ground-based systems, known as terrestrial LiDAR, provide extremely high-resolution measurements, up to the even millimeter accuracy, for detailed studies of forest structure, archaeology, and engineering applications. These systems are ideal for small-scale, intensive studies, but are limited in their spatial coverage. There are also aircraft and unmanned aerial vehicles, or UAV platforms, offer a balance between resolution and coverage. Airborne LiDAR typically achieves point densities of 1 to 50 points per square meter and is widely used for topographic mapping, forest inventory, and hydrological studies. Third, satellite-based systems like NASA's JEDI and ISAT-2 provide nearly global coverage, but with lower spatial resolution. These systems are essential for understanding large-scale patterns in vegetation structure, ice sheet dynamics, and global carbon cycles. Modern LiDAR systems employ different technologies to capture and process laser returns. Discrete return LiDAR systems record individual return pulses when the laser encounters reflecting surfaces. A single laser pulse may generate multiple returns as it interacts with different canopy layers and eventually the ground. Discrete return systems typically record about 1 to 5 returns per pulse and are common in airborne applications. Single photon counting LiDAR systems, which include NASA's ISAT-2 mission, detect individual photons rather than complete pulses. While providing less energy per measurement, these systems can operate from much higher altitudes, including space, and offer unique capabilities for ice sheet and vegetation studies. Instead of recording discrete returns or individual photons, full waveform LiDAR systems capture the complete energy profiles, called waveforms, of the returned laser pulse. This provides more detailed information about the vertical distribution of reflecting surfaces and is particularly valuable for vegetation studies. The entire waveform can be analyzed to extract multiple metrics describing canopy structure. Our training today will focus on this latter category of full waveform LiDAR. First, we'll talk a little bit more about discrete LiDAR. For discrete LiDAR systems, return pulses are classified into one or more discrete returns. These returns are recorded when the intensity exceeds a predefined system threshold. And that intensity is shown here on the x-axis as returned energy. The last returns are especially important for detecting the ground, where you can see there may be 1 to 5 returns. And here in this schematic, we can see that the 4th return here corresponds to what's called the ground return. Now let's discuss some differences in terms of the spatial sampling patterns of discrete versus full waveform LiDAR. The decision to choose one system over the other involves a trade-off between the level of vertical detail captured and the achievable spatial coverage for a given project. In essence, full waveform LiDAR excels in providing intricate vertical information at the cost of reduced spatial coverage, while discrete LiDAR can often allow for prioritizing a high density of samples due to less detailed vertical information. Here is an illustration from a study in Taiwan of the spatial coverage differences between a full waveform dataset from JEDI, which has the rich vertical profile data, and discrete return airborne system, which has, as you can see, nearly wall-to-wall coverage. So the JEDI footprints correspond to the light green, ISAT-2 observations correspond to the black dots, and the airborne laser scanning data, or the ALS data, which was used for validation purposes for this study and is the discrete system, is shown in the brown points. Instead of just recording peaks, as in the case of discrete Lidar point clouds, full waveform Lidar systems capture and digitize the entire profile of the returned laser energy. This results in a continuous waveform that represents the vertical distribution of all surfaces the laser pulse encountered. For the example shown here, in a forest, the shape of the waveform reveals the height of the canopy, its density, and the location of the ground beneath it. This detailed information is exceptionally valuable for complex vegetation and biomass studies. Now we will move to section 2, which focuses on full waveform LiDAR from the JEDI mission. NASA's Global Ecosystem Dynamics Investigation, or JEDI, produces high-resolution full waveform LiDAR observations of 3D structure of the Earth. JEDI is deployed on the Japanese experiment module exposed facility. The highlighted box shows the location of JEDI on this part of the International Space Station. This diagram shows how JEDI's 3 lasers work. One laser is split into 4 coverage beams, shown in blue, that create 4 ground tracks. The other 2 full power lasers, shown in orange, are not split and create 2 ground tracks each. In total, this creates 8 parallel tracks of data collection on the Earth's surface, separated by about 600 meters. JEDI science data products include footprint and gridded datasets that describe the 3D features of the Earth. These data products are assigned different levels, which indicate the amount of processing that the data has undergone after collection. All products are publicly available, with the lower level products, level 1 and 2, from NASA's Land Processes Distributed Active Archive Center, or LPDAC, and the higher level, level 3 and 4, are from the Oak Ridge National Laboratory DAC. Data are initially transferred to the JEDI Mission Operations Center at the Goddard Space Flight Center that deploys acquisition planning on a weekly basis and then processed through the Science Operations Center to distribute science data products to the DACs. The physical theories, mathematical procedures, and model assumptions that are used in the creation of these data products are described in what are called the algorithm theoretical basis documents. These documents can be found at the link provided in the slide here, which then these slides will be posted again on the training website. In today's training, we are focused on the level 1B and level 2A data products. So the level 1B data are the geolocated waveforms, and the level 2A include the ground elevation, the canopy top height, and what are called relative height metrics, which we will get into in the next slide. This is a representation of a waveform, which contains information about both the vegetation canopy and the underlying topography. A near-infrared pulse, in the case of JEDI, is fired towards the surface of the Earth, where it is reflected by leaves and branches within a nominal 25-meter diameter footprint, which is shown on the right. The returned waveform, which is shown on the left, is processed to find ground topography, canopy height, and relative height metrics. Relative height metrics quantify the vertical structure of vegetation by calculating the height at which a specific percentage or quantile of the total laser energy returned to the sensor is reached relative to the ground surface. So in this case, what you can see here from this waveform is, although there is some small amount of energy here, we would consider that noise, and we'll talk more about noise in the demo. But from this waveform, the height at which all of the energy of the waveform is returned to the sensor occurs here, and that's known as relative height 100. So 100% of the energy of the waveform has been returned by this height. Similarly, relative height 50 is the height of median energy. In other words, this is the height at which 50%, so this amount of energy has been, this lower part of the waveform has been returned to the sensor, but still 50% of the remainder of the waveform energy has not been returned, right? So RH50 is by definition lower than RH100. So now let's take a tour of a real-world example, level 1B waveforms from JEDI that we will be looking at in more depth in the hands-on demo after this presentation. Here is an example of a waveform from JEDI's level 1B dataset plotted in Bankhead National Forest in Alabama. We are looking at an area of the forest where some of the trees in the stand appear brown, indicating damage and possible mortality of the trees, which is likely due to the presence of Dendroctonus frontalis, the southern pine beetle. And the southern pine beetle is currently widespread in this region. The trees within the highlighted yellow example footprint in the forest appear mostly green. Looking at the corresponding waveform plot to the right of the map, the first peak of the waveform that you see circled in brown corresponds to the laser energy returns that reached all the way to the ground, since these correspond to the lowest elevation peak. In this case, there is a range of high amplitude above ground returns starting around elevation 180 meters, all the way up to about 210 meters. The observed wide distribution and multiple peaks of returns along this elevation profile could indicate the presence of some healthy trees and intact branches in the shot, despite widespread beetle infestation in the immediate surrounding area to the north. Here is another example of JEDI level 1B waveform plotted in Bankhead National Forest, so in the same general region, but a slightly different track of data. From the waveform plot, we can see very low amplitude signal in the above ground return. The lack of high amplitude returns higher up on the elevation profile could possibly arise because of low tree cover and/or tree mortality within the footprint of the shot. You might be wondering, though, that at least from the satellite image base map, it seems like at least most of the area within this 25-meter diameter footprint, the trees appear green. Although in the satellite Esri worldview base map that we are using here, we see some green trees, it is important to note that there might be a temporal disconnect between the satellite imagery base map that we're using for reference and the JEDI shot we are looking at here. The imagery for the Esri worldview base map is stitched together from various different acquisition dates, and the exact acquisition date of this image could be anytime between 2019 and 2024. Meanwhile, the JEDI shot here is from 2019. So there may have been some tree recovery and/or regrowth captured in the optical satellite image that is not what's shown and represented by the time slice that the JEDI observation reflects. Here is a third example of JEDI level 1B data. The waveform shows a single ground return with no above ground signal whatsoever. In this case, we can see from the base map that this actually makes sense, where this footprint is in a sparse vegetation area featuring grass and small shrubs, but no trees in the 25-meter diameter area. So it's very possible that the small amount of grass or very small shrubs were not picked up by the waveform signal at all. Let's look at a final example. In this case, we see multiple peaks of the waveform, but it is unclear from visual analysis, at least, what portions might correspond to the ground versus what portions of the waveform correspond to vegetation above the ground. When you explore these data in an area of interest of your own, using, for instance, the Python notebook that we will be looking at in the upcoming demo, you will notice that some waveforms show clear, sharp ground returns with minimal activity below. However, other shots will show more complex patterns, such as the one we are looking at here, where we can see multiple peaks in what we think is the ground return or the initial part of the vegetation signal. The good news for us is that in the level 2 data processing, shots like this would likely be clarified through an additional set of processing where there are 6 different algorithms that all contribute to identifying where the actual ground is. And if these 6 algorithms don't agree within 2 meters, they are generally excluded from subsequent analysis. The most common reason for a complex or unclear ground signal could be due to noisy measurements, either from system noise or from thermal noise. Another possibility is that there may be more heterogeneous terrain within those footprints. On sloped terrain, the 25-meter Jedi footprint may sample across elevation gradients. Combined with Jedi's geolocation uncertainty, which we'll mention in a later slide, the assumed ground elevation may not represent the true ground within the footprint. And then a third potential reason is that different vegetation density might be affecting scattering, where laser photons can scatter multiple times within vegetation before reaching the detector, arriving later than expected and appearing at lower elevations than the actual ground. So you may remember seeing this figure before when we first introduced the idea of the waveform. Now we are seeing a third plot which shows the cumulative energy returned at each height as a percentage of the total energy of the waveform. So this is called the cumulative return energy profile, with percentages converted to cumulative probabilities that range from 0 to 1. So the RH metrics that we already defined, that we're circling back to now, quantify the vertical structure of vegetation by calculating the height at which a specific percentage of the total laser energy returned to the sensor is reached, relative to the ground surface. So as you can see here, RH95 canopy height is often defined as RH95, but can also be up to RH100 depending on the particular application. Here's an example of canopy height data from Jedi in the region of Ucayali, Peru. The rectangular areas are oil palm plantations, and the surrounding areas are a mix of mature forest, secondary forest, actively used pastures, and abandoned pastures. In this case, canopy height is quantified as RH95, although, as I mentioned, RH98 or some other similar upper RH metric could also have been used. Notice that there are some points along the tracks of data that are excluded. That is because we applied a standard filtering procedure that removed any observations with a low quality flag. Low quality data could be instances of observations that either did not meet the beam sensitivity threshold of 0.9 or that showed a deviation, as I mentioned before, greater than 2 meters among the 6 algorithms used to identify the ground elevation. This graph shows the mean and standard error of relative RH metrics in the cumulative energy profiles for different forest classes in Ucayali, Peru. We can see the mature forest class shown in blue, the secondary forest class in dark green, and the young vegetation regrowth, which is generally in areas of abandoned pasture lands, that is shown in light green. We see that mature forests have the highest canopy heights and the lowest variance in canopy height relative to secondary and young vegetation regrowth. And this is pretty consistent across all RH metrics, not just these upper metrics, which correspond to canopy height. Meanwhile, RH50 corresponds to the height of median energy, as we learned in the previous slide. And this metric, RH50, tells us about the distribution of understory vegetation, which also varies by forest type. Among the forest classes, again, we see that mature forests have the highest RH50 values relative to secondary and young vegetation regrowth. RH metrics can be compared across land uses. Here is that same data set that we saw on the previous slide from Ucayali, Peru, showing the median and interquartile range of relative height metrics of interest over tropical lowland forest regeneration classes, which we saw on the last slide, including mature forest, secondary forest, and young vegetation regrowth, typically after pasture abandonment. And then we also see some agricultural classes, including oil palm plantations, as well as cacao plantations, including both monocrop and agroforestry cacao systems. Despite their power for capturing detailed vertical structure, spaceborne full waveform LiDAR systems like JEDI face numerous operational limitations. One limitation is geolocation error. JEDI has positional uncertainty of each footprint of about plus or minus 10 meters for a 1 sigma error. This requires careful filtering and the use of buffers, especially in heterogeneous areas where a footprint might incorrectly sample an adjacent land cover type. A best practice is to filter JEDI observations to only include footprints with homogeneous land cover types of interest within a diameter of 45 meters, say, 25 meters of the original diameter area of the beam, and plus or minus 10 meters additional buffer to account for geolocation error, as shown in the figure here. Another limitation is the inability to fully penetrate clouds, which, unlike other active sensors that are radar systems, LiDAR systems aren't able to penetrate clouds. Another limitation is that in exceptionally dense canopies, such as tropical forests that we saw in the Peruvian Amazon, the laser signal can be entirely attenuated, in other words, absorbed or scattered, before it reaches the forest floor, resulting in an inability to detect the ground. And as a part of the level 2 filtering that we did in the examples that I showed here, this limitation was accounted for by the filtering that we applied. Another limitation is that the data is collected in distinct footprint tracks rather than a continuous map, leaving large spatial gaps. This comes back to that difference that we were talking about earlier between many airborne discrete LiDAR systems versus spaceborne full waveform LiDAR systems. So essentially, this makes the data unsuitable for applications requiring wall-to-wall coverage of a region. Another related limitation is that of limited temporal resolution. Due to the spatial sampling of the JEDI mission and the sparse spatial sampling, it is very rare for any of the JEDI footprints to be repeated and observed by a second time. There are some cases where this happens, but there are not very many over the globe. Finally, another limitation is slope-induced waveform contamination. In areas with steep topography, the large laser footprint can hit the ground at different elevations simultaneously, distorting the shape of the return waveform and complicating the identification of the true ground surface. Before we move into section 3, which will focus on practical forest ecosystem applications with JEDI full waveform data, we now have a 15-minute break for questions. I will start by addressing question 1, which I believe was asked during the conversation about discrete versus full waveform LiDAR and airborne versus spaceborne LiDAR, if I'm correct. And the person who asked this question can let me know if I'm appropriately addressing it. So the question being, does the platform and fine resolution of airborne LiDAR sensors, is what I'm inferring here, guarantee accurate biomass estimates in temperate and boreal forests? So the short answer is no. While airborne LiDAR provides more accurate estimates than spaceborne systems, it does not guarantee accuracy due to numerous fundamental uncertainties. So Airborne LiDAR is more accurate than spaceborne for a few reasons. One is the reduced geolocation error, as we talked about. The other is the higher point density. And then finally, there's generally better ground penetration. So lower altitude and denser sampling increase the likelihood of being able to detect ground returns, especially in dense canopies, which I guess more applies to tropical forests than you were specifically asking about temperate and boreal forests, where essentially with denser canopies, spaceborne systems may experience complete signal attenuation. So that is the first question. And then question 2, why do we use RH98 for canopy height and not, say, RH100, for example, right? So, and then the second part of that is, what is the possible application of RH50? Does RH0 correspond to ground elevation? So great questions. So let's start with the question about canopy height. This relates to the fact that there is often noise as a part of the the spaceborne LiDAR waveform that causes RH100 to be an artificially high estimate of canopy height. So, and this does vary shot by shot. So that's why there's no single RH metric that across the board is used as canopy height, right? It can be RH95, it can be RH98. Generally, I haven't seen, for most spaceborne LiDAR studies, I haven't seen folks use RH100 just because of that, the reality that a lot of times the noise is present and not fully processed out in level 2 data processing of JEDI data.
And if I can add something to what you're saying, Savannah, this is
sure.
Sometimes RH100 doesn't capture the canopy surface, depending on the resolution that you want to study. Say you need to characterize the canopy surface with 30-meter resolution, right? And you might have a JEDI shot that is centered on one very tall pine tree that has a sticking top, and that is going to drive your RH100 up, right? That's going to be your RH100 essentially. So that doesn't really represent the canopy surface at the resolution you're trying to study. So that might be another reason, in addition to noise. It might be like a real return, but it's coming from an outlier tree, and it's not necessarily how we want to quantify canopy height.
Yeah, thanks for that addition, Nayara. And let's go into the, and unless there's follow-ups about that, we can go into the question about RH100, which is the height of median energy of the waveform. So because these RH metrics, they reflect and the waveform itself reflects the amount, the distribution of biomass along the vertical profile. When we look at RH50, for example, we can learn about the understory in a way that can tell us about how much vegetation how it's distributed, right? So, for instance, in a forest that has, and since someone did ask about temperate forest, maybe we could use that as an example. If there's a temperate forest that has a denser understory, which is allowed, can often happen when the taller trees are more separate, and that allows for light to get through to the understory, that will be detected by higher RH50 values. And whereas if there was less of an understory, maybe those RH50 values would be lower. So that's just one example. Nayara, I'm not sure if you'd like to add to that explanation as well.
No, nothing to add. Thank you.
Okay, great. And the question about RH0 is a good one, because actually, I wonder, in the follow-up, when we post this question and answers document to the course website, I can add a visual that might help explain or kind of speak to this question about RH0, because some RH metrics, often RH metrics in the level 2 data, JEDI data, are negative, meaning that they're part of the ground return energy. But as you saw in the one of the previous slides that was showing kind of this waveform, showing the multiple waveform examples, you'll notice that a lot of the energy that reaches the ground, due to a couple of factors, and I could get into them, but I also want to be mindful of time, that essentially some of those returns will end up being registered as below zero ground surface. So sometimes RH0 is negative, and sometimes it is around zero, and sometimes it's slightly, and so I think it varies on the topography and on the level 2 processing algorithms that are, where there's basically 6 different algorithms that are used, at least in the JEDI data processing pipeline, all of which are designed to identify the ground and have slightly different ways of doing that. Anything to add, Nayara?
No, nothing to add. Thank you.
Sure. So what is the global availability of this data? Great. So we already have kind of an explanation here where for JEDI in particular, which is on board the International Space Station, and due to its placement on the ISS and the ISS orbit, there is a bounding of latitudes between 51.6 degrees north and south. So that's where the data are available. And then, as of course mentioned in the presentation, this is a sampling mission, right? So it's not wall-to-wall coverage, and neither is our other Lidar, spaceborne Lidar missions from NASA, right? So ISAT is also not wall-to-wall coverage. So sampling, they're both sampling missions. So question 4, since Lidar is an active data collection platform, why is it limited by cloud cover? This is a good question. And so I think maybe another thing to think about is that there are different types of active sensors, and Nayara's expertise is actually in radar remote sensing. So Nayara, maybe you could also speak to this, because radar systems are able to penetrate clouds. But JEDI, which fires in the near infrared portion of the electromagnetic spectrum, that wavelength essentially often does not penetrate through clouds. And so that's the short answer. And Nayara, if you want to elaborate more and kind of explain how radar systems are able to penetrate clouds, I think that would be really helpful for the audience.
Yeah, essentially the active has to do with whether the instrument makes its own signal or not. And then the issue of signal penetration depends on the wavelength. So you have LiDAR that can't penetrate through clouds. And radar, you also have different wavelengths, and some of them can penetrate through canopies and some of them can't. So that's why we usually talk about the wavelength when you're characterizing those systems. So the issue of sensitivity has a lot to do with how the signal penetrates in different media. So this is a very good question.
Question 5, you stated the green band penetrates water. Can it be used to study water pollution from an industry like mining? So that is an interesting question. I'm not aware of applications. It's not my area of expertise, and I wonder if we could do a follow-up on this question to kind of look a little more. I mean, in terms of Lidar, I don't think there would be an application for water quality. I think the water applications of, for instance, ARSET, which fires in the green, is more for detecting quantities of water and changes in ice. So for Lidar specifically, I'm not sure that there would be an application for water pollution the way that, you know, optical sensors are used. But I'm learning things every day. So, you know, it could be. So I think that I'll leave that as my answer for now. And if anyone else wants to chime in, Nayara, or yeah, we will follow up.
Yes, we will follow up and look for some references.
Mm-hmm. Is there any filtering applied to filter out shots with clouds? So this will depend, for JEDI specifically, this will depend on the level of processing. I believe in Nayara's demo actually focuses on level 2 data, so maybe you're more refreshed up on the exact filtering steps in the different levels. But for level 1B, which is what the upcoming demo will focus on, I believe there's no filtering. It's up to us essentially to apply the filters. So there's no pre-filtering when you request the data. All of it will come back. But then there are 2 different quality flags which we'll learn to use, and then those will help with the removal of observations that may be contaminated from clouds.
Sometimes you also see a canopy height that is unusually high. So you see RH95 that's like 200 meters, and that might be an indication that that's an area with clouds. So one simple thing that you can do is to threshold the RH95 and say, you know, just consider shots where RH95 is the maximum canopy height in your study area. Then you would exclude buildings as well. So I'm assuming we're interested in vegetation and land cover, but not buildings.
That's a great point. How can JEDI be used to estimate or identify deforestation? So JEDI can be used to, JEDI can, you know, tell us about the presence of trees or lack thereof, right? By the waveform, you know, returns that we see. And so if we only see, actually, in one of the examples I gave, we saw a very, you know, a sparse area, which I think was mostly grass with a few shrubs, that all there was in the waveform signal was a single ground return, right? And so that's an indication that there's no forest, right? When the you know, when there's no amplitude above the noise threshold for above the ground return. Question 8. Are there some types of forest that JEDI is not able to fully penetrate and thus not reaching the ground? If so, how is that detected and how is the structure analyzed? Great question. So tropical forests are the type of forest that are most where this happens most often, right? Where there's such a dense canopy and understory that it is possible that none of the energy of the laser pulse reaches the ground. And in that case, the level 2 algorithms, I believe, that are applied, and we will follow up just to provide more details on this, but essentially, like I said, there's 6 algorithms that are part of the standard JEDI processing pipeline that their job is to identify where the ground is. And so there's a number of different ways that we could identify cases like this where there is no ground return identified. And one of the ways is by looking at these 6 different ground algorithms. And if there's greater than 2 meters disparity between them in terms of their calculation of where the ground is relative to the reference geoid, then that will be a flag, right, and excluded as from the in the quality filtering. So for now, maybe we can go into the demos, and then we'll have a second Q&A session after the demos, and we'll do our best to address as many questions there. And then those that aren't addressed, we will answer all of them and post the Q&A document on the course website. We are now starting section 3, which focuses on practical forest ecosystem applications with JEDI full waveform data. Exercise 1 has 2 objectives. First, to enable participants to access, filter, and visualize JEDI Level 1B full waveform data using NASA Earth Data Application Programming Interfaces. And 2, to teach interpretation of waveform characteristics for vegetation structure analysis. In this hands-on demo, we will start by authenticating with NASA Earth Data login credentials. Hopefully everyone has their Earth Data account already set up. And then we will search for JEDI Level 1B granules using the Earth Access Python library. We will download JEDI data for the specified area of interest, apply quality assurance filtering using the quality flag and the degrade flag fields. So there's 2 different fields that we'll be searching for. Then we will plot raw waveforms for multiple footprints. We will identify and interpret ground return signals versus canopy returns. And we will analyze waveform morphology to assess vegetation vertical structure. This will be over the same region that we saw in the slides that have been presented, which is focused on Bankhead National Forest, Alabama in the USA. The default latitude and longitude bounding box can be changed to your own area of interest if you clone the GitHub repository and modify your local copy of the Google Colab notebook. So for this demo, we will be using the default AOI, but I encourage you all to modify to your own area of interest, either now or in the future with the code. We will focus on the entire set of observations collected to date from the JEDI mission, starting in April 2019, all the way to up into through October 22nd of this year. All right, let's get right into the Python notebook. Now I'm going to walk you through a Python notebook for processing NASA's JEDI Level 1B full waveform LiDAR data. As a reminder, JEDI collects detailed 3D information about Earth's forests and topography from the International Space Station. So this notebook demonstrates how to search for, download, quality filter, and visualize the JEDI Level 1B waveform data for a specific area of interest. This is the README file for the repository. And we will go ahead and it does list all the steps of setup, but we will just walk through each of these steps together in the Google Colab environment. So we will just click on this button here on the top of the README file. And this will bring us to the Python notebook shown here. We'll start with step 1, which is to clone the GitHub repository. And this will allow you to access this notebook and any supplemental files with this step. So we'll press play here. That allows the cell to run. You can just click run anyway for the warning, because it was not the script wasn't authored by Google. And this is what the output would look like. Once it says 100% done, you can go into the next cell here, which involves installing the required libraries. So there's a few necessary Python libraries. We will use pip to do that. So Earth Access is a library that we are using for authenticating with NASA and searching the data archive. H5Py is used for reading JEDI's HDF5 file format. GeoPandas library is used for spatial data operations. Matplotlib and Seaborn are both used for creating visualizations. And then finally, Folium is used for interactive mapping. So let's see how we're doing here. Once we see at the bottom of the output that all libraries were imported successfully, we can move on to the next step, which is to mount your Google Drive. We can run that cell. And in order to do this, you need to be signed into a Google Drive account or have an account that you can sign into, where you will connect to Google Drive and choose the account that you want to use, pressing continue. You might have to do this twice. That happened for me during one of my installation setups. It will run for a bit. When that's done successfully, it'll say mounted at, and then it'll say content/drive. In this next part, we will authenticate with NASA Earth data. You'll need to enter your credentials when prompted. And again, these are free and can be obtained from earthdata.nasa.gov. And actually, before I run the cell, I also just want to highlight in the code here that we are using the default AOI, which the area of interest is in William Bankhead National Forest and the surrounding area in Alabama. If you would like, during this demo, either now or there will be time after we go through this first default AOI example to update this bounding box, note that there's, then you will be able to do that. And note that there are 4 coordinates that you need to enter here to change from the default to whatever area of interest that you want. And so what you would need to enter is the minimum longitude, the minimum latitude, the maximum longitude, and the maximum latitude of your area of interest separated by commas. So I'm gonna go ahead and run this cell where you'll see that we are prompted to enter our Earth Data login username and password. And once that happens, the rest of the cell will run. I'll also point out that we have a temporal range defined here as, all available Jedi data available to date. And then the search for the data starts by focusing only on full power beams. And this is to increase the chance of having high quality data. So in the data when we apply the filtering that we apply, a lot of the data from coverage beam lasers gets removed. And so we want to just focus on the power beam for now. And so what this function does is the search Jedi level 1B function takes the input bounding box that we provided, the temporal range of the data that we are wanting to search for, and then also a maximum results list just to put a cap on how much processing time we're going to take to retrieve some of these data. Once those files are returned, there is a step of extracting the data. And so we will go ahead and just look at the output here in the interest of time. This is what the top of the output looks like, where we can see our longitude and latitude range, and the focus on just the power beams, which are listed here. Here are the granules that were retrieved. It was again a maximum of 20 that were searched for this time. And for this code, for the purposes of the demonstration, it will stop at the first granule that has some quality data. So if this first granule, this is the name, the full name of the file here, the HDF file. But if this were to have no data, then the code would automatically try the next file down on the list. And this can take a little while, the queuing, specifically the processing step of processing the data, because each file can be several gigabytes. So in this case, the HDF5 file that we're looking at is 4.19 gigabytes. So each one takes a while to process. And for the purposes of this demo, there were several files on this list that didn't pass the quality flag filtering and didn't have quality data and were skipped. And so I wrote something into the code that if it's the specific bounding box that we're using for the demo, it will skip straight to this fifth file on the list. So for those who might be paying close attention to the code, I might have noticed that. I just wanted to say that in general, if you put a different area of interest, it will go in order file by file until it finds one with at least some quality data to analyze further. Here is a summary of each of the beams, how many shots were retained after the quality filtering step. And as you can see here, in all of these full power beams, 100% of the data were retained. So overall, we have 335 shots across all beams. This section of the notebook generates 4 different visualizations. So plot 1 is the shot locations map. This shows where each Jedi shot landed, color-coded by elevation using a terrain color scheme. This helps us understand the topographic variation in our study area. Plot 2, to the right here, shows an elevation histogram. So this displays the distribution of elevations. The shape tells us about the local topography. A narrow peak suggests flat terrain, while a broad distribution indicates varied terrain. And as we can see here, most of our shots fall within 250 and 300 meters of elevation. So that's a pretty narrow range. Plot 3 shows shots per beam. This is a bar chart where it indicates data availability across the full power beams. So an uneven distribution is normal due to JEDI's orbital geometry and data quality. And then finally, we can see a pie chart here, which is the processing results pie chart, summarizing how many files were tried and their outcomes: successful, no spatial data, or no quality data. And as I mentioned before, many files don't have 100% quality data, but for the purposes of this demo, I'm using an example that does. Moving on to level 1B waveform visualization, we will first produce an interactive map where you will be able to look at the AOI boundary, zoom in and pan around the study area, and then click on individual points to see shot details. You'll also be able to distinguish between different beams by color and then understand the spatial patterns of JEDI coverage. So let's go ahead and run this cell. So it will take a little while to run, and our output will be shown down here. First, we see a quick summary of the user configuration. I'll note that there is a function that is called select shots by elevation deviation and in this code segment. And this function selects shots based on standard deviations from mean elevation. That allows the user to define different standard deviation values that you'd like to focus on in the plots. So there's just 10 shots of the 335, in this case, total shots that are going to be plotted. And so which of those 10 shots are plotted is up to the user to define as based on what elevation they would like to focus on. In the default of the code is currently written here. I'll just show that we have negative 0.5 standard deviations. So in other words, the 10 shots that we're plotting in the waveforms will have slightly lower than average elevation among the 335 shots total that were extracted from the HDF file. So here we can see the interactive map where the lowest elevation shots are shown in dark blue and blue, and the medium to high elevation shots are shown in green and red. And as I mentioned, we're showing slightly lower than average elevation shots, these 10 shots highlighted on the map. And all of those are in the blue, colored as, well, are in the blue category, but are highlighted in yellow so that we can see spatially where each of these coincide into. And then we can pan in and out, whatever zoom level you'd like. And let's look into an example the same example that we saw from one of the slides in the presentation, which is shot 2, where you can see by zooming in, I believe this is the maximum zoom level that's allowed here on this map, but we can see that basically this is a pretty sparse area. There aren't any trees within this shot, and there's what looks like either grass or small shrubs in this footprint. So now let's take a look at the waveform that corresponds to this particular footprint that's highlighted. And in order to do that, we'll need to put the cursor inside of this cell and then scroll down to see the plots below. So these are the 10 different plots that were selected, again, as a based on the standard deviation that we put in. And they're numbered here, where we have plot number 1 corresponding to the footprint 1, and footprint 2 is the one that we zoomed in on above here in the map, which has a lot of bare ground and very short vegetation and grass, which basically shows up as what looks like a single ground return with very minimal indication of above ground vegetation. On the other hand, we can see this waveform to the right, or also we could look at to the left. Let's look at both of these. So shot number 3 to the right is showing a ground return. Looks like a pretty clear ground return here, and then some evidence of above ground vegetation with most of the waveform amplitude right above the ground return, but then some non-noise returns of the waveform appear a bit higher up in elevation from that initial second pulse. So let's take a look here on the map for looking for footprint 3. So if we zoom out here and look into footprint 3, and again, if we click on the footprint, we can see some of the information about the beam and shot number, as well as the elevation, latitude, longitude. And so what we can see from the base map is it looks like there are some healthy trees within this footprint, which makes sense given that we saw above ground returns. And if we zoom out a little bit, you can see that darker shades are in the surrounding neighboring area could be evidence of beetle infestation. And we know from colleagues that we collaborate with who study these regions that these beetle infestations, the South Pine beetle, have been very prevalent in recent years in these forests. So if we zoom out again and this time look into waveform number 1, we can see that the forest does begin right after 2, right? Looks like there's an edge here where there's more of a thickly dense canopy, and by this first footprint here, or footprint number 1 here, we can guess that there will be at least some above ground vegetation returns. And like I mentioned in the presentation, we want to be wary and cognizant of the fact that the base map that's used here is from the Esri Worldview satellite imagery composite, which comes from different dates and based on, best optimal cloud-free acquisitions, and is kind of stitched together that way. And so we don't have a way of knowing exactly, at least not with the script written here, what the temporal difference is between what we can see on the base map versus when the Jedi waveform was plotted, which, as you can see from the file name, 2019 was the year that was plotted, and then this is the Julian date. So here we see waveform footprint 1, where there's a clear ground return and also indication of above ground vegetation that has, as shown by the kind of multiple peaks of higher elevation returns that are above the waveform, or above the ground return rather, and below the kind of remaining noise of the signal past around 210 meters or so. So we looked at a couple of different waveform plots and their corresponding locations on the map here. I would encourage you to go back into the code and modify the standard deviation that you use to select the 10 waveforms that you'd like to plot. So for this example, I'm going to increase this to 2 standard deviations above the mean, and then run the cell. And rerunning this cell is going to produce a different set of results that we'll take a look at. We'll take a little bit to rerun. I would like to say that for those of you looking at areas of interest that are different than this default AOI, you might notice that changing the elevation, especially if it's higher elevation shots, these might be areas these might be more noisy or more noisy shots, or shots that waveforms are, or maybe more difficult to interpret. In this case, there's some elevational gradient, but not a ton. So with the 10 different examples that we're looking at here, if we scroll down again to the 10 waveforms, we can see that in all of these cases, there seems to be a clear ground return, except for this one, which I believe was the same example I provided in the slides. And in areas that have even more complex topography than the area that we're looking at here, I would anticipate higher elevation areas to be associated with waveforms that are, challenging to interpret, such as this one. And so for now, in the interest of time, I will conclude this demo. But please feel free to note any questions that you have and share any ideas for future improvements with the code. And yeah, so all your feedback is always welcome. And with that, I will pass to Nayara to look and to walk us through exercise 2.
Thank you, Savannah. So we are going to do an exercise processing Jedi Level 2A datasets using the NASA Harmony tool. And our goal is to display relative height metrics for vegetation structure analysis. And the basic steps are to order the datasets, to do a spatial subsetting, and then we're going to import the results into a Google Colab notebook. We're going to do some filtering based on existing quality metrics and then display in QGIS. So we're going to get started by looking at the repo and opening the Colab notebook. So let's get started. We start by navigating to the VegMapper repo. And when you get there, let's go to the JEDI folder. That's where the routines for processing JEDI datasets are located. So we click here, and we want to use the JEDI L2A underscore ARSET. So we click on this notebook, and it should have a button that says Open in Colab. And if you are not signed into Google at this moment, it will prompt you to sign for Google. We're using your Google account. So once you get in the Google Colab notebook, the first thing to do is to install the packages and the dependencies. So we're just going to run these two cells without changing the inputs. And it will take a minute, but Google Colab has already many of the libraries that we need, and we don't need to install them. So let's wait a minute. You can disregard the error messages here, and let's just move to the next cell where we import the packages that we need. And the main one to keep in mind is the Harmony package, which gives us an API to connect to the NASA deck and request the spatial subsetting of the JEDI orbits. These are some really large files, so we're trying to do the spatial subsetting in the cloud, and so we just download the smaller files. Now we need to authenticate with Earth Data. If you haven't signed up for Earth Data, you can do it. It's free. So I'm going to put my credentials here. And if your credentials are up to date, it will give you a green check mark. Then the next thing to do is to upload my area of interest. And I'm using a GeoJSON file, which I'm going to import here into this area. So I'm going in my local files and importing into, you just drag the file into Collaboratory. And now when we press play, it's going to request the path to this file, and you can click on those three dots here, copy the path, and then paste here. So essentially it's in a folder called content, and this is the file name. So check, make sure that the GeoJSON is correct. You might have an issue if your shapefile or if your GeoJSON has too many vertices, in which case you have to simplify it. But what we have is just a square. So it was accepted with no issues. I can show you briefly where the site is and how big this area is. This is Brazil, and the site that we're working with is in the Atlantic rainforest in the southeast part of the country. And I picked this site because it has a very nice variability in structural signatures that will help us gain an intuition for what the relative height metrics are giving us. So you have here some water, some forest fragments. We also have some agriculture here and some urban areas. And we have a ton of bare ground. So the expectation here is that the top height is going to show us the differences between forest fragments, tall versus short, and also between forest fragments and farms. So for step 4, we're going to define the date range for the subsetting. And we're also going to define where we want to save the results. So if we run this cell, I'm going to put the entire range of Jedi observations from 2019 to the present day. And I'm going to define a folder to save my results. So I just want to save here in this content folder. So again, I go to the 3 dots, I copy my path and paste it here. So that's where the files are going to be saved. Next step, I'm calling the Harmony client. And for this size of area of interest is going to take about 10 minutes. And in the interest of time, I'm going to bring the resulting files here. But when you run yourselves, please wait 10 minutes and you're going to see the files being generated. So for step 6, we're just saving the file. And because I already have my file, I'm not going to run this cell, but if you run the Harmony cell and you wait the 10 minutes, you have a file there and you can run the cell to save the files in your folder, and it's going to look like this. You're going to have a text file, and if I open it, it doesn't have the Jedi datasets themselves. Those are just links, and each one of them is a file in H5 format. So for the next step, we're going to define how we're going to further filter these files. And I'm going to use some criteria that are commonly applied to this level 2A dataset. So if I run this, one of the criteria that's commonly used is the sensitivity. And the sensitivity is the maximum canopy cover through which the lidar can detect the ground with 90% probability. So because I'm working in a forest, a tropical forest, I'm going to set this to 0.9. And then the minimum RH95 value, this is if you want to, for example, exclude areas where you have a canopy, a height equals 0. So I usually put 1. And then true or false, do you want night only? I'm doing false just to get as many shots as possible. But one way of getting data sets with more signal to noise ratio is to select night only. But for now, I'm just going to put false. So we will get shots from daytime and nighttime. So I selected my inputs and then they got checked here, and we can go to the next step. So now we are running the main function that does all the filtering. It's going to download all the H5 files from the file list, and one by one, it's going to apply the filtering using the criteria specified on step 7. And then everything is going to be combined in the end in a single CSV file. So for this cell, we don't need to do anything. We're just running to get the function. Okay, so at this point, we're just running the function, and we're just going to choose the location of the input file. So to get this file, you just click on the 3 dots here and copy path, and then you paste in this box. And now we're going to choose where we want to save the resulting CSV file. So what I'm going to do is to copy the path for this folder and then add the file name that I want to use. So it's up to you. And then it will take about 10 minutes to do the processing. I do have this file generated already. So what we're going to do is to move to QGIS to explore the data. And to get this to QGIS, you would click on the three dots and download the file. And then we can bring it into QGIS as a vector layer. So let's do that. So we're going to add this layer to QGIS. Just choose a delimited text layer. And we just navigate to location of your file. And QGIS will try to find the latitude and longitude columns for you. So it just guessed and it was correct. So we'll just say add. And close. So here are my shots. Now I want to just change the display to show RH95. So instead of a single symbol, I'm going to have graduated symbol based on RH95. And let's change the color here. And we click on classify. So this is the range in my data. It goes basically from 1. Remember, we asked to filter out things that are shots that are lower than 1. And maximum canopy height here is about 24 meters. You do have some outliers. That's not uncommon. I would filter out shots where RH95 is over 60 meters or 80 meters, depending on your forest. So let's apply. So now looking at this landscape, the first thing to notice is that you have somewhat irregular sampling of the landscape, right? You don't have a wall-to-wall image, but it's still giving you very important and interesting information. And you can see here that each one of the dots has a value, which has the maximum canopy height for my forest fragment. And the areas of bare ground look orange and red, as expected, because they have lower canopy height. And the forested areas have a higher value. And you can also see some variation between forest fragments. Some of them are taller than others. And you would need to make some assumptions about the spatial variability in this landscape to be able to derive metrics at the patch size, right? Because as you can tell here, we're not covering the entire patch. This area here is an agricultural zone, is a sugarcane. So the height is between 3 and 6.2 meters, which makes sense. You have also shots in urban areas. This is an area that with not a lot of buildings here, so about 6 meters for houses. And again, the red with low values for bare ground. So it's always good to have some bare ground as you're trying to get used to this data set to get a reality check. But of course, your base map can have a temporal properties that don't match up with the Jedi shots. So we need to keep that in mind as well. And the other thing to keep in mind is that sometimes you don't have shots in the forest. You can almost see like the beam is being interrupted, and this is happening because we filtered them out, either because sensitivity was low, or because you might select nighttime only, and the beam was acquired during daytime. So one thing that can be done for each one of your sites is to experiment with the filtering variables. And I know for other modules of this tutorial, this is going to be discussed in more detail. So thank you everyone for your attention, and I'm available to answer any questions that you might have. So with this, I'm going to send this back to Savannah, and Savannah, you can summarize the discussion.
Thank you very much, Nayara. Now, we will move into the summary of Session 1, Introduction to Full Waveform Lidar. Let's review the key concepts from Part 1. First, we covered LiDAR fundamentals. LiDAR is an active sensor that measures distance by timing how long laser pulses take to return. This gives us detailed information about elevation, canopy height, and the three-dimensional structure of vegetation. We learned that full waveform LiDAR, unlike discrete return systems, records the complete energy profile of each pulse. This captures the entire vertical distribution of vegetation within JEDI's 25-meter diameter footprints, providing much richer structural information. The JEDI mission operates from the International Space Station with 8 parallel laser tracks. It covers latitudes between plus and minus 51.6 degrees and produces both footprint level data at 25 meters and gridded products at 1 kilometer resolution, which we'll talk more about in the upcoming session 2. A major focus of today's session was relative height metrics. RH95 gives us canopy height. RH50 tells us about understory characteristics, and the ratios between these reveal canopy layering and structural complexity. These metrics are powerful for distinguishing forest types and land uses. We also discussed important limitations. JEDI has about 10 meters of geolocation uncertainty. The instrument also can't see clouds. It provides discrete sampling rather than complete coverage, and has limited temporal resolution for any given location. Finally, you gained hands-on experience accessing NASA Earth data, downloading and filtering JEDI data, and interpreting waveforms to understand vegetation structure. These are the foundational skills you'll build on in parts 2 and 3. Looking ahead to part 2 of this training, you will be able to describe the general characteristics, strengths, and limitations of the JEDI mission and its data, identify JEDI data products and their characteristics for elevation, canopy height, vegetation structure, and biomass. Access and visualize JEDI datasets, including elevation, canopy height, vegetation structure, and biomass for an area of interest using openly available tools. This is a list of resources that were cited throughout today's presentation and also could be useful future reading after this session. I'd like to remind everyone that there is one homework assignment for this 3-part series course, and it will open on the day of session 3 on November 6th, 2025. The due date for the homework will be 2 weeks later, which is on the 20th of November. You can access the homework from the training page, and note that your answers must be submitted via the Google Forms. If you attend all 3 live webinars and complete the homework assignment by the deadline, you will receive a certificate via email about 2 months after completion of this course. Here is my contact information, as well as the contact information for Nayara Pinto. And also linked on this slide is the ARSET website and the ARSET YouTube channel. With that, I thank you all so much for your participation today and look forward to seeing you next session in part 2. And now we will move into the second round of Q&A. All right. Thank you all for adding more questions into the document here. I will start by talking through some of the questions that came up that were specific to the demos. And we'll see how far we get in the 15 minutes that we have. So let's go with part 1B. Question 1 was a question about how can JEDI level 1B data, which is in HDF5 format, be converted into a shapefile using code, or what is an alternative method to achieve this conversion? So the demo script does extract the coordinate data and then the attributes from the HDF5 file into a pandas data frame. So that's in what's called result._df. And then to convert that to a shapefile, you can add a few lines of code following the data extraction. And in order to do that, the library we recommend using is GeoPandas. So you would need to import GeoPandas, install and import, and then convert the pandas data frame to a geodata frame. And then this is the code that you could use to export that GeoPandas, the geodata frame, into a shapefile. But that said, I do want to highlight alternative formats that are vector-based, formats, but have some advantages. Specifically, GeoJSON is a great option, which is great for web mapping, and there's no file size limits. The GeoPackage format has no attribute name length restrictions, which shapefiles do. And then we also kind of talk about CSV as another option. So because of the limitations of shapefiles, both the character field name limit of 10 characters and having multiple files as opposed to just one, that's one of the key advantages of these other alternatives that we're listing here. You could consider, replacing the shapefile with one of these options. Okay, let's move into question 2. Is RH98 available with the level 2B data or only with level 2A data? So all RH metrics, including 98, are available in level 2A only. Level 2B are which the next training actually will cover more, right? So this training actually didn't discuss level 2B data. That is canopy cover and vertical profile metrics. So basically more processing is used on the RH metrics to create derived products, such as the plant area index, which is essentially analogous to leaf area index. I'm not sure if you all are familiar with LAI, but that is the area, the leaf area plus the woody vegetation, the woody biomass area per unit ground area. That's the definition. And then foliage height diversity is another example of such derived products in the level 2B. And so the next session we'll discuss more in depth all of these derived products. And so the RH metrics, though, specifically are just the level 2A data. Question 3, can I do the analysis in a heterogeneous urban environment? So technically, you can obtain data from JEDI over urban areas, right? So the NASA APIs will not prevent you from doing this, but there are very big challenges and important caveats to think about. So JEDI was designed and optimized for vegetated ecosystems, particularly forests. And So starting with the plus or minus 10 meter geolocation uncertainty, combined with the heterogeneous land cover of urban areas, means that a Jedi footprint, right, with a 25-meter diameter footprint, might sample a tree, a building, a street, or a mix of all of these within that footprint area. So a best practice, which was discussed in slide 38 of our training, is to filter observations to areas with homogeneous land cover within a 45-meter-ish or so diameter, right? And so that accounts for the 25-meter footprint plus a 20-ish meter buffer for geolocation error. And the 10 plus or minus 10 meters comes from kind of the 1 sigma error. So if you want to be more conservative, you can add a slightly larger buffer, or you could be, less conservative if you want to be able to have smaller kind of buffer zones. So, that's up to the individual researcher and research project needs. But that's the general rule of thumb, right? So in urban areas, you would want to apply this strict spatial filtering to ensure that these footprints are sampling vegetation only. So for example, maybe you could study a large park in an urban area, or a street that has lots of trees and it doesn't have many buildings that are right up against the street, right? So to be able to cover that large of a buffer area. And then you could essentially exclude shots in your buildings and carefully interpret the results, since the waveforms may be contaminated by non-vegetation returns. So hopefully that explanation provides some is useful as you think about urban areas and just really thinking carefully about the caveats before moving forward with that. Question 4, and Nayara, please chime in at any point if you'd like to add on to any of these explanations. So question 4 is it looks like there was a warning. So in my collab environment, I'm getting the following dependency conflicts when running the pip install code cell. So pip's dependency resolver does not currently take into account all the packages that are installed. This behavior is the source of the following dependency conflicts. So these dependency conflict warnings are common in collab environments, and usually your code will be able to run even with these dependency conflicts. So if the notebook ran successfully, then that basically means that the version differences in these dependencies won't break functionality. And in that case, I would just recommend you can ignore the warnings. There are a couple other ways to address this. So one is to restart the runtime in Colab, and then kind of rerunning the cells from the top of the script. So this can resolve some issues. And then there's also a way to kind of specify the versions of what pip is installing. So here's an example of a way to do that, which I'm highlighting here. And then there's also a way to run, the pip install command to specify no dependencies. So that's -- no -deps flag. So, and you can do that if you know other dependencies are satisfied. So essentially, in summary, for training purposes, if your code runs and you can authenticate and download Jedi data successfully, you can safely proceed despite these warnings. They're primarily informational and won't affect the Jedi data processing functions. All right, let's get into question 5, which asks, why do you think plot 6 in the 2 standard deviations example had a much more complicated structure than visually similar plots like plot 1? Is this potentially a factor of slope? Or likely just a more complex structure underneath the canopy? So this is a really interesting question. And just to kind of elaborate a little bit more about what I think this first part of the question is talking about. So the much more complicated structure that we saw was specifically where it was unclear just from visual inspection of that waveform where the ground return was and where ended and where the vegetation began, right? And so and then it's great that this participant, you know, thought of a couple possibilities as to why this is happening, right? So one question was, could it be slope or could it be more complex structure underneath? And the answer I have is that both factors could contribute to this complex waveform structure that you're seeing. So we discussed this on slide 38, where slope-induced waveform contamination is a known limitation. And so you can imagine we have a 25-meter footprint, right? And then if there's a lot of steep topography within those 25 meters, the laser pulses will hit the ground at different elevations simultaneously, distorting the waveform shape and creating multiple peaks. So that could be happening, right? And then you can also think about ways to determine which of these factors is dominant by checking the elevation bin zero values and examining whether there's a significant kind of terrain variation within the area. And then you can also look at the degrade flag for the shot. So if the 6 ground finding algorithms disagreed significantly, so more than 2 meters, then it would be flagged and might indicate slope contamination. That said, complex waveforms can also genuinely reflect real vertical structural complexity, where if we have multiple canopy layers, especially dense understory or heterogeneous vegetation in the footprint. So the example on slide 33 showed how the ambiguous waveform with the multiple peaks can result from either terrain effects or actual vegetation complexity. So if the particular area in the footprint has relatively flat terrain based on a digital elevation model that data set that we could look at, then the complex structure is more likely of a possible reason why there was real canopy, you know, the real canopy architecture with multiple layers or close to the ground could be happening. Great. So question 6 asks, is it possible to access the JEDI data and use the functions shown in the exercises using the R software package? R software packages. Is there an equivalent of Harmony for R to allow spatial subsetting of the orbits prior to download? So yes, R users can access and work with JEDI data using the R JEDI package, which was developed by the JEDI science team specifically for processing JEDI data in R. This package provides functions to download JEDI data from the LAN processes DAC, read HDF5 files, extract metrics, and perform spatial and temporal filtering. For Harmony-like spatial subsetting capabilities in R, you could try the HARP R package, which provides an R interface to NASA's Harmony services and should support spatial subsetting of JEDI granules before download. And this, I haven't actually it's been numerous years since I've used R for this kind of functionality with JEDI data, so I'm not sure, you know, what the up-to-date versions look like and what's been developed in the past couple years. But I think that HARP R should still be working. And there are also other kind of standard R spatial packages like R HDF5 for reading HDF5 files, and SF for spatial operations, and Terra for raster operations can also, you know, work well for this.
And one thing to add here is that in addition to the language, another thing to keep in mind is if you're running this in your local laptop or in the cloud. So one critical step here is to download files from the repository, right, from NASA DAC, and then you're doing the subsetting. And we did this in Colab because we wanted to do this in the cloud. So you're avoiding downloading very large files into your laptop to do the subsetting, or to do the filtering, I should say. So Harmony is doing the subsetting for you. So that's another thing to consider. And in Colab, of course, you can implement things in R as well. So
yeah. So we're coming close to the top of the hour here. So I'll answer question 8. So it looks like question 7 was a repeat of 5. So you can see that explanation which we covered. Question 8, is there a legend planned for the future that explains the colors, line types, and axis labels? RH25, RH50, RH75 appear as labels, but without any explanation of what they mean. And then there was an example here of RH50 is the height below which 50% of the reflected energy was received, median height of vegetation. So that is actually, in my explanation here, I'm going to address that because that's actually not quite correct interpretation of RH50. So let's start actually just with the overall point, I think is that for lay people, and it sounds like this participant is specifically in public health applications, just looking at a graph without much interpretation of a waveform is not, it's not interpretable. And that's, I think, an important point about thinking about how we can make JEDI data and visualizations more accessible to interdisciplinary audiences. So I really appreciate that, the question and the intention. I do want to quickly clarify a distinction that, so the first part here, so RH50 is the height at which 50% of the cumulative energy return has been received. So that's the height of median energy of the waveform, not necessarily the median height of vegetation. Just want to clarify that. And just to further elaborate a little bit, is it just that the energy distribution reflects complex interactions between laser penetration and canopy density throughout the vertical profile. So it's probably related and close to median height, but not exactly, and it could vary. So the training addresses waveform interpretation through annotated examples that we provided in slides 30 through 33, right? So we added interpretations directly onto the figures where we were circling where the ground returns were versus where above ground vegetation returns were, explaining how with multiple peaks, there's likely an understory as well as a canopy height corresponding to the top, the tallest elevation peak, and then we talked about the cases where there's just a single ground return and how generally that corresponds to areas where there aren't any trees in the footprint, the sparse vegetation or bare ground. However, hard coding these interpretations into the automatic plotting of the code would create issues in terms of broad applicability and reproducibility across different forest types and conditions, and across the different standard deviations even, right, that we plotted. So we wanted to make the code flexible and versatile for adjusting the areas of interest, adjusting the standard deviations that we're using to select which waveforms we wanted to plot. So that's why we kept the demo code plotting functions just generalizable and basic in terms of the axes that we have, and not refraining from labeling the waveforms directly. But for other interdisciplinary uses, they're developing materials for non-remote sensing audiences, I think would certainly benefit from adding custom annotations to plots with, for example, matplotlib, and creating supplementary documentation. Or on your own, you can copy this code from the demo and then modify the code and the plotting functions to include text boxes that do explain the key features, if that's something that you'd like to do. All right, we are now a few minutes past the hour, so I think that's going to be the last question that we'll answer in real time here. But look for the Q&A document where we will fill out answers to all the questions that we receive. And I just want to thank everyone again for your participation and looking forward to seeing you all next week for session 2.
Thank you, everyone. See you next week.